Pero no vamos a hacer un certificado de...
Pero es que a lo mejor entre que lo grabamos sale una cosa que...
Sí, no, a mí me parece bien eso.
Si está, se graba.
Pero ya sabes que son multitud.
Pues lo sabéis, pero es fundamental.
Cuidado,
Gente constructiva.
Ah, sí, sí, sí.
Cuando necesitamos que el vídeo peñada.
We have Peter Samuelsson. He did the postdoc in Geneva with me and with David long time ago.
Yes, long time ago. Yeah. Mm-hmm. Yeah.
And then he moves to.
Well, no, we collaborated, right? yeah.
Then he moved to Lund, where he is there.
Yeah, right.
And he's expert on quantum transport and quantum thermodynamics and electricity and many other things. And yesterday he was part of the committee, Phys committee of the student in the museum. He became a doctor. And well, so it's a pleasure to have you here and to listen to you.
Thank you very much. Thanks for the kind introduction, and also thanks for the invitation. It was really nice yesterday to be in the committee and be allowed to ask a lot of nasty questions. I think the defendant answered well, so everything went straight and nice. So thanks for the invitation. I would like to talk about some work which is rather recently published, and this is together with an experimental team in Helsinki, Finland, Jukka Pekola, who is a really great guy on doing experiments on nanoscale and quantum thermodynamics, and his PhD student, Karimi. And the person here who should be mentioned, who did most of the work, is actually my own student, PhD student, Brange, who is soon defending. Actually, Rosa will be in the committee there, so you can pick up some of the information from here. So there is a close connection experimentally, and I come back to this picture here. I just put it on the front page. It's a theoretical work, and there is a picture of the system we are proposing, and then some Monte Carlo simulations of how things could look here. But let me come back to that. So the outline is as follows. I will try to start on a rather basic level and say something about what calorimetry is of heat pulses. This is actually something that was unknown to me also before I started to work on this. So if there are some experts on calorimetry here in the audience, you might think that I'm not really getting the full picture here, but I hope I will be able to tell you a little bit about what the background is. And then something about the nano side of what people have been developing over the last decades, how to do fast and very sensitive measurements of the temperature in small systems, and then some of our estimates for what you would need in order to detect very low energy things, for example, electrons who are tunneling in a small conductor, or photons of a microwave field that have in the gigahertz regime where we'd like to detect them by these calorimetric methods. So this is the outline of this ideal case. Then I will describe what type of system we are proposing. And this is based it's based on a combination of normal and superconducting metals. So rather conventional technology that the people in Finland are very good at manufacturing. And I would describe a little bit how the theoretical model looks and explain that it connects very well to the experimental equipment that they are presently measuring on. And then I will be a little bit more technical and talk about our methods to calculate and present and investigate this system, about energy transfers in the system, and then the resulting fluctuations of temperature here. So I will warn you when I get to the more technical parts here. But I will try to start in a more easygoing way, and this is about calorimetry here. So a good start is maybe to go to the source of common information here and just see what is calorimetry if I look on Wikipedia. So if I just read out loud here, it says that this is the science of measuring changes in state variables. So we remember our thermodynamics. You can have the temperature, for example, in this case, or some other state variable of a body for the purpose of deriving the heat transfer which is associated with the change of its state. And that can be due to chemical reactions or physical changes and so on. And we will consider the case where we want to put some particles or some energy, heat quanta, and measure the change of the temperature of a body. So this is the very basic version of what a calorimeter would be. So you have a piece of material, which is your absorber. That is where you want to absorb the energy that you have transferred. And then you add at some point some source, and you, in this case, a small flame here, so you start to heat up this one, and then you measure along the way what happens to the temperature of this body here. And if we assume that this is evenly distributed and so on, we can just think of a hypothetical temperature curve. We start here, and then we start heating, and the temperature rises, and then we take away the heat, and then it levels out at some other constant temperature. And then we can see, how much higher is the temperature after we have done this, and then we can use our thermodynamic knowledge and say that the energy that was absorbed by this block of concrete, in this case here, is just the heat capacity of the system that we probably know or might know, multiplied by the change in temperature delta T. So that's the overall idea of a calorimeter, classical calorimeter. Then, where does the word quantum come from in the calorimetry? Well, as far as I've been able to detect, this seems to be coming from high energy physics, when people were interested in having a way of measuring the energy of elementary particles banging into some detector of some kind. And it was one of the ways you could try to do it. And then the idea is kind of the same, but we can go a little bit more refined here and closer to what I'm interested in. So let's think of this stuff here as some schematic picture. The blue stuff is an absorber, so that's your material where your elementary particle bumps in. Here it comes. It has some energy E, the red one here. And this absorber is typically connected to some background. And if you use the language of thermodynamics, this is some bath, some huge thing which has a well-defined temperature. And you again have a thermometer connected to your absorber, and then you look over time, and at some point, pound, comes this particle. It's absorbed, and as I will explain more later, you assume that the energy is immediately spread out into the system and converted to a change in temperature. So your thermometer jumps, and then after it's jumped, well, then of course this absorber is somehow connected to the background. So there's a thermal conductivity. There's a small sketch here showing the absorber and the background, and then some thermal conductance or thermal resistor if you want to here. And as a result, then your temperature starts to decay exponentially down towards the background temperature again. And in the ideal case, when the shift in temperature is rather small compared to the background temperature, and you don't really worry about any sources of noise here, you will just get this very simple exponential decay. So you, at some point, you have a step, and then you decay exponentially. And then the decay time scale here, decay time, is set by the heat capacity of the system divided by the thermal conductivity between the absorber and the background bath there. And I will come back more to what the microscopic reasons can be for this, but in any case, if you have two bodies close to each other, different temperature, you will have a flow from the hotter to the colder. And you can do the same now. You look at this peak, and then you get the energy of the incoming particle as C, your thermal capacitance multiplied by your temperature shift here. So now, this was the overall idea, and the quantum there comes from, well, you're doing this for individual quantum particles. So that's where the word quantum comes from here. And then in the field of nanoscience, where I'm mostly working here, then this idea was also implemented and used to building small-scale devices. You can have more sensitive, faster, better working things when you work on the nanoscale. And it's fair to say that there was a large development maybe in the 90s and the first decade of the 2000s here, when people developed and made these things better and better. They are typically, I should mention here now that what has typically been made has been what you call a bolometer. So I talked about calorimeters before, and a bolometer is something which is a little bit different. Sometimes you see them interchanged, and it's sometimes a bit confusing. But the way I will talk about them is that a calorimeter has one single pulse, boom, that lands in your system, and then you try to see what energy that pulse contains. While a bolometer means that you have a constant flux of something in, which establish your, as you see here in the picture, when the flux is on, you have one temperature of your system, and then when you turn off the flux, you go back to the background temperature. So this is a little bit different, because in the flux means that you have zillions and zillions of individual particles or small quanta of energy that enters into your absorber here. So it's somehow a more crude version, if you want to, of this individual quanta. But that's how things started in the nano field. People just demonstrated this for detection of X-rays. There is a sketch here, I'm not going into this, but I'm just mentioning that it's typically built out of metals where you have superconducting and normal conducting pieces ordered in a certain way. Some of the arms come from some antennas sending in the signal. Some of the arms are essentially your thermometer. So it's kind of an integrated circuit where everything sits here. And here there's a picture in this experiment how they did. They have an artificial heat pulse, so that at some point they just turn on the radiation in a stepwise manner, and then they see the temperature responds very rapidly, and then they wait for some time, and then you turn it off, and then you find that your temperature decays, and that decay constant is just as for the calorimeter. It has to do with the thermal connectivity between your, let's say, detector piece, which is this small yellow stuff in the middle, and the background. In this case, it's the entire substrate in the system here. And people learn to do this fast, and what is fast? Well, fast means that you can follow in real time the development of the temperature. And that depends on all these constants of the system. But you see, in many of these cases I will be talking about, you can talk about a time, a relaxation time, or a temperature decay time of the order of microseconds. So you need to have some equipment that can measure the change of temperature of a small piece of metal on the order of the microsecond scale. So it's fast, but compared to many other processes that we see in nanoscience, it's actually not so fast. We sometimes talk about nanosecond scale or picosecond scale, and this is now microsecond scale. So it's actually a rather slow process compared to many other mesoscopic ones. If there are questions, I'm happy to try to take them on the fly here, see if you want to. Okay, and there was also, I'm mentioning another work where people were able to increase sensitivity. And this has a little bit been the development now, right? People have been, and here I'm actually summing up some recent findings by the people that we are collaborating with experimentally. They have a set of papers recently where they have made things smaller, faster, better, but not really fundamentally different, I would say. So this is still a bolometer in the sense that you look at the constant flux in. Here you have some signal, you send in some AC signal or some electromagnetic radiation, and then you turn it off, and then you see what happens to the temperature. So here it's a picture where you have, let's see if I get this right now, I think there is the red one I think is a normal metal, and the blue one here is some superconductor, and then you have some contact here. This is actually your thermometer, and then you have a heater to the left, and you have your electrical ground to the right, and then it's coupled to a resonator, microwave resonator, which is a technique of doing fast measurements. So this is a micro graph of how it really looks. It's clearly nanoscience. I mean, this is 1 micron, so this is kind of, 200 nanometers thick and so on, and wide, and I don't know exactly the dimensions of it otherwise, but it's a rather small thing here, right? So when you do it smaller, you can actually have a smaller heat capacity, which is more sensitivity to the, let's say, larger temperature swing for the same energy. And you can also hope to reduce the noise, and you can hope to make the thermometer fast. And this is a point where we are assuming that it's essentially non-invasive. You measure temperature, and somehow you need to disturb the system, but we are not so quantum-ish here that we have to worry about that you are disturbing the system by doing temperature measurement. And it's actually the readout process itself, we think we are in a regime where it doesn't really destroy the system it's going to measure. But that will eventually be a problem if you really push this down even further into the deep quantum regime. And I'm just giving you some parameters here. They might not say so very much. First, it tells you that the heat capacity, it has this interesting property of having the same dimensions as Boltzmann's constant. I never really thought about this before when I started to look at this. So the typical thing is to say how many kBs is your heat capacity. So this is now 10 to the 3 to 10 to the 5. That's where they are for the moment for this size of systems. And it's microsecond time scale for the decay. And the background temperature, it depends a little bit on how good they are, but they can have an effective temperature of the background, which can be down to 30, maybe even lower millikelvin. So it's somehow a thermometry done at very, very low temperatures. And the question is then, can we really take these systems where they typically do mostly bolometry and with these type of values for the parameters, can we really push this to do quantum calorimetry? Can we really look at individual tunneling electrons? Because the heater can actually be turned into something which contains a tunnel barrier so that you are providing heat by tunneling in electrons. Or you can send in individual photons. You can create microwave photons with such a diluted stream so that you can get them one by one. Can you do this and measure their energies with the help of these type of setups? So this was the question that we asked ourselves when we started this, and we wanted to do some let's say back of the envelope calculations to see whether we were in the right ballpark. Okay, and then you need to think not only about you need to go a little bit more detailed into what happens in the time regime when you do this absorption of one small quanta. And one thing we realized pretty early on was when we are pushing things down so far that we have very, very small energy quanta corresponding to individual tunneling electrons or microwave photons, we can no longer ignore the fluctuations that come from the fact that you have a microscopic mechanism of, in our case, phonons, which are carrying the heat from your absorbing piece of metal to the background. So this is actually a transfer of small quanta of energy carried by phonons, mainly. And therefore we said we have to somehow worry about that, because if these background fluctuations due to the exchange between the absorbing material and the background becomes too large, we won't see anything from the signal that we want to have. And here we did some Monte Carlo simulations where we kind of simulated in a very simple way this process where the heat pulse happens at time 0, so there's a big thing. And then on top of that, you have all these oscillations which are coming from that you are really treating the phonon transfer of heat between the bath and the absorber quantum mechanically as a small individual events. And the red one looks pretty good. You would still be able to say that you had something here. And that's a rather small background fluctuation amplitude. By the black one, then, you are actually having a much larger one. And I would probably say that most people looking at the black one only would say, well, we don't really see much here. Right? So this is just for the eye. And the way we try to estimate this is that we say, okay, there is actually for this transfer or for the temperature fluctuations, you can actually go back and look in the books of Lund and Lifshitz. If you prefer, in their statistical mechanics, they derive something which is a fluctuation dissipation like relation. And it's a little bit like in the sense that it's a fluctuation of temperature, and if you have fluctuations of other quantities like what we are used to, electrical currents and so on, temperature enters, but here it's a fluctuation of the temperature itself of some system. And then you can say that the time-dependent correlator has some prefactor, and then it has this exponential decay I talked about before. And then you can say, well, let's look at the amplitude of these fluctuations, the prefactor here, how large is the fluctuations momentarily here, and take the root mean square, and you can get a value out here. And that we like to compare to the size of the temperature swing due to the heat pulse we are putting in, let's say, which we want to measure. That's our delta T, which is the energy over C, energy of the particle or the quanta over C. And then we can define something like a signal to noise ratio, say that our homemade quality estimate of this. And if I put in the parameters which I gave you before, maybe going towards the more positive side of things, then we can see that if we really push things and have an energy corresponding to the gap of an aluminum superconductor, I will come back to this, that would be an electron that tunnels from above the gap of a superconductor into a normal conductor. If I take a very low capacity, 10 to the 3, 1000 kb, and if I really push my temperature down to 5 millik, which is probably at the borderline what people can do, then I get the red curve here. And if I instead take this to be 30 millik, which is more reasonable, then I get the black curve, and that's when it starts to become a bit difficult to do. So we realize here that there is maybe a small window of opportunity where you can push parameters here and have a chance of getting that. So that was kind of the first estimate. Well, I also say here this energy would correspond to a 50 gigahertz microwave photon. And typically people in the business would like to go a little bit lower also there if they can on the energy of or the frequency of the photons for various reasons. So one thing we realized is that, okay, we have to be careful with the background. We have to worry about the fluctuations. And it might even be a little bit too complicated to go directly on an experiment where you see these time-resolved fluctuations as a first attempt. It's really where the experimental community wants to go. That's kind of the goal. You want to see individual particles. But what we said is that let's maybe take this step by step and think about, can we say something about the fluctuations and how things behave in this type of system beyond that we require to resolve every individual event, that beyond or less ambitious than having this single shot readout. And that turned out to be the main course of our investigation here. So, and if you want to, the investigation of the single shot readout theoretically somehow stops here, right? I mean, here we have the numbers, and the rest of the problem is for the experimentalists to push their parameters down into this regime. But if you want to worry about the fluctuations, one can actually ask more interesting theoretical questions, and that's what we did here. So
this
yeah.
temperature is related to which observable of the absorber, like a population inversion or something like that?
So the temperature, the T of E here is the temperature, the electronic temperature of the absorber. Yeah. So that would be in this picture here, typically the red one, or in my cartoon, if I go back, it would be the temperature of this blue one here. And it's the electronic temperature. So the electrons are the ones who, let's say, take the hit of the particle first, and then they thermalize individually. I will come back to this a little bit later also. And then they talk to the phonons in the absorber and also down in the substrate, and that's kind of the process when the heat leaks from the electronic system to the phononic system.
Yes, this is about the transfer. I was asking more about which is the observable that is really going to be measured.
The observable, there are, the observable is temperature, and of course the temperature is observed based, you don't read out temperature directly, you read it out from some other way. And one way which people have used quite a lot, which is actually showed here, is an NIS thermometer, and that's something you use. You apply a bias on a normal insulating superconducting contact, and then you get an IV curve. And that IV curve you know from other calibrations that this has a very characteristic dependence on temperature. So then you can read out the temperature from that IV curve. You can put yourself in some operation point, and then you would, around there, you can see that you are very sensitive to temperature changes. That's one way. The most recent thing, which I didn't go into here now, that the people in Alto did, was that they were able to do a thermometer which is based on a modulation of a Josephson current. So it's a dissipation-less current flowing through parts of the absorber region. Let's say you have some additional contact, so there is a Josephson current, supercurrent flowing through, and that one has a very characteristic dependence on temperature. So you're reading off the magnitude of an electrical current, and then you translate this into temperature. So it's a good point. Temperature, I mean, even a thermometer that you wave in the air is of course something which is based on some secondary mechanism, right? Yeah. Okay. So this was the point that we realized that we want to explore things that can be done as a step towards this ideal calorimetry, and we wanted then to look at the, let's say, what can we say about the fluctuations? And then now I start to become a little bit more technical. Let's see if I can have you along here without losing you completely. It's also after lunch now, so it's a bit dangerous to be too complicated. Let's see. So the idea is now that we say, okay, if we are now assume that it will be hard to resolve every individual pulse, let's then see what is a little bit more feasible, namely to look at a set of pulses coming over a longer time. And this is a little bit, let's say I wrote down here, it's like a hybrid version. It's not a calorimeter in the sense that it's a single shot measurement, but it's also not really a bolometer because we take into account the discreteness of the individual events coming in here. So the red one here means something that jumps into the system which has higher energy than this would be a set of fermions. This would be higher than the chemical potential. But you can also have situations in a nanosystem where you are actually losing energy. You can have a hole tunneling, or you can have some particle tunneling out, such that you remove some energy also from your absorber. So we want to treat both possibilities, the events that add energy, which might be the one we are looking for, but we might also have transfers of, let's say, phonons and other mechanisms that eventually remove energy a little bit. So we want to allow for discrete particle, discrete events treated quantum mechanically, but they can work in both directions in terms of the removing and adding energy. And then we say, well, let's look at this for a reasonably long time, so we have many pulses, and then we can talk about the probability distribution that if you measure during 4 seconds, every time you do a measurement, you will have a different result because the underlying process is stochastic. So you might have different outcomes in how much energy you have observed or you have gained or lost during this period of measurement. And this can give you a probability distribution, which will depend on the, let's see here, which will depend on the energy that you are, which is the total, sorry, the E is the total energy. It's a proper distribution of total energy, which will depend on the temperature. If you do this for it should be short enough interval here that your temperature of your absorber is roughly the same here. So everything will depend on what temperature of your absorber is. It will be typically close to your bath temperature here. And this is now a mathematical way of writing a probability distribution in terms of its Fourier transform. And then I don't know to what extent you are familiar with this, but that's a trick or a way that we are using in nanoscale and mesoscopic transport, that we write probability distributions in terms of cumulant or moment generating functions, which are very practical to work with. So as I said, this is a bit more technical. And we are also assuming as an input for our analysis, which I think matches well to the experiment, namely that the transfer statistics of these events is a Poissonian one. So you have a set of it can be electrons tunneling or it can be phonons jumping, but they are in a system where they are all weakly coupled, so your transfer of individual particles will be some Poissonian process. And then we can write this generating function in a convenient way in terms of the distribution of the individual energies here. So this is the technical tool we are using. Okay, let me say something about the system we are looking at. So we are focusing on the case where the heat pulses comes from electrons which tunnel. So we are not looking at the case with microwave photons, so it will be tunneling electrons. And here is the sketch of how it's a simplified version of what I showed you before, and doesn't really look the same, but this is a simpler way of showing it. So the green one is now some metal, which is the absorber. The blue are two superconductors. The one here has some temperature that you can vary, so also you can tune the temperature of your, this is, let's say, the injecting part where you want your particles that you are looking at come to tunnel from. And here this gray says that this is a tunnel coupling, so there is a weak coupling between the superconductor and the absorber. The yellow one is a thermometer, and I'm not going to say anything more here, so I'm going to duck on the question of exactly how the measurement is being performed. We assume that this is for all practical purposes something non-invasive. So it just measures the temperature, T over T here. And then this one here we also don't really have to worry about. This is another superconductor which blocks energy, heat flow out, because this heat cannot flow under where energies, you cannot have any heat flow towards the superconductor if all your energy scales in the absorber are smaller than the superconducting gap. So this is the nature of the superconductor that this is blocked. And this is also well coupled here such that the electrical potential of the absorber is anchored to the electrical potential or the chemical potential of the superconductor here. So there are some assumptions made which I summarize here. So the point is that we will study elementary electrons jumping from the superconductor into the absorber, and then we will see what happens to the temperature fluctuations on the absorber. Here is a circuit also when we draw this in a little more qualitative fashion, and then we also include here the coupling between the electrons in the absorber and the phonons, primarily the phonons themselves inside the metal in the absorber here. And they have some coupling constant sigma. So this is another parameter that we need to know. And we also actually need to know the volume of this one in order to calculate the properties we need. So we have a set of parameters. I'm not going to say very much about that. There is a tunneling conductance between here, which we need in our calculations. There is this phonon coupling constant. And then there are in principle 3 different temperatures. So it's the background temperature, which also this superconducting contact has here. There is the temperature that you might use here on the superconductor if you want to heat that one. And there's also the electron temperature, which is the quantity we are looking at here inside the absorber. Yes, and this is what I mentioned for the other superconductor here, right? It's a good contact which works as a heat mirror and suppresses any fluctuations of the electrical potential here. So, something about the time scales we are assuming here also, and which I would say are motivated in our case. So here is a picture of what happens in the system where you have a particle tunneling into your absorber. So the green distribution here shows that at some point, when we start looking, there is an energy quanta, or there is a particle tunneling in, which has some certain energy, and the first thing it probably does is that it leaves its energy so that you have some small peak in your distribution at the energy where it tunneled in. Then, on the time scale of interactions between the electrons in the absorber, this energy is distributed among all the electrons. So you thermalize your system. So after this short time scale, the electron-electron interaction time scale, you typically have a thermal distribution. But this temperature of this thermal distribution is typically higher than, in this case here, than the temperature of the background is. And then on another time scale here, which is the time scale when you transfer energy from your electron system to your phonons, then the red one here will slowly cool off until it eventually reaches the temperature of the background. So this is a thermalization to the lattice or the underlying structure here. And it's important now that this is the fastest time scale. So the electronic interaction in this metal should be super fast. So the particle comes in, and without we having any chance of reacting, or we don't even account for that in the system, the temperature is immediately established. So we always assume that we have a well-defined temperature, and we have thus a very well-defined electronic distribution in the system, the Fermi distribution, with this temperature. So this happens momentarily. This is an approximation, but it's typically a good approximation in the systems we're looking at. But then this temperature fluctuates, and then this time scale tau comes into the game. And if you really want to do calorimetry, you would like to have well-separated pulses, but in general, we can actually treat also a situation when pulses might come on top of each other. So this is not really important for the case when I'm looking at the fluctuations and not the individual events. Then there are some detailed assumptions for the experts. We don't worry about the so-called proximity effect in the superconductors, and we assume that we don't really have any unwanted heating, so that if we apply a voltage bias across the system, we don't really affect the temperature of the superconductor, the injector superconductor. None of these things are perfectly okay in the real world, but this is kind of some theoretical approximations which are reasonable. Okay. So then, some technical information about the injecting side here. So then I wanted to treat the two cases. We have the injection of particles from the superconductor into the absorber. And then I'm using some formulas which are, I say, standard if you're in the business for looking at tunneling between a normal metal and a superconductor. There are some spectral rates which are known since the 60s. And there is a superconducting density of states, and there are the Fermi functions. And you can plug them in, and then you can do some tricks, which are that you are adding extra factors which are called counting factors, or they contain the counting fields, which are the reciprocal numbers to the total energy transferred. So this is a way of obtaining the full function which counts the the energy transfers across the interface between the superconductor and the normal conductor. You could also count the charges, but we don't really need that now. We are only interested in counting the energies transferred with each individual particle tunneling. So this is the function, and it's picked down into a form which contains, let's say, well-known things. And this cumulant generating function has the nice property, well, it generates the cumulants in the sense that if you take repeated derivatives with respect to this counting field, you will get the different cumulants of the transfer. So to first order, you will get the average energy flow, and to second order, you will get the fluctuations of the average, fluctuations of the energy, and so on. So this is the tool that you use for this complete statistical description of all the electrons that tunnel back and forth across this interface here between the superconductor and the absorber, between the injecting part of the story. Well, then we also point out that you can actually tune your applied bias, or you can tune your applied temperature on the superconductor such that you can get situations when your particles which are being transferred are very well defined in energy. So you can get your particles to be essentially only injected just above the gap of the superconductor, and you can suppress tunneling way outside of that regime by choosing certain parameters. This is maybe a little bit more detailed information. The point here, so the take-home message of this slide is that you can tune by temperature and applied bias. You can tune the energies of the particles tunneling out from the superconductor and into your absorber, which is nice if you want to use this as a test where something is well known. So I just don't dwell longer on that, but go to the next path. The next thing we wanted to treat now fully quantum mechanically was the transfer of heat between the electron system and the phonons in the system. And then we have a similar model. You can essentially go and look it up in some standard condensed matter textbook. What are the spectral rates, and we are considering the case when there are a three-dimensional metal, and these are just standard phonons in the metal. And then you can calculate the transfer, the spectral rate for exchange of energy with these phonons with some Fermi distribution on Fermi-like distribution on one side, and then you have some Bose-Einstein distribution of the Bose distribution of the phonons here on the other side. This is some set of harmonic oscillators with some frequencies. And then the volume V, right? And then you can do the same calculation as on last slide. We can calculate all the events. We can account for all the individual events of transfers of phonons, where energy transfers across the interface, which destroys or creates phonons. So then we can calculate again the cumulant generating function, and we can calculate the various cumulants out from that. And this is also more of a technical detail here. We can get some results which are almost exact for all these cumulants here. But that is maybe not the detailed, interesting information. You can use this to extract some known results about the energy, current, and noise to a bath of phonons. And you can also look again at the distribution of the energies of the phonons which are going between your bath and your absorber. And then you see that this distribution of phonons is much, much more broad and, let's say, stretches over a larger energy space than the one with the superconductors. The superconductor, you can really trim it to be at some specific energies depending on your superconducting gap and your very sharp density of states in the superconductor. But the phonons, there is no such energy scale. So then you will just have some rather broad distribution. You see that if you have the same temperature of your bath and your absorber, your distribution, this dashed black one, will be completely symmetric. You will inject and remove energy in the same way. But of course, if your bath is hotter than your bath is hotter than your absorber, you will have more phonons which have high energy than with the low energies. Then you have an asymmetric distribution here. So this describes the emission and absorption of phonons in your bath here. Okay, temperature fluctuations statistics. This is also maybe a bit technical, but I'm getting to the end of the presentation here. So what we can do now is that we can use this information. So far we calculated the distribution of fluctuations under the assumption that the temperature of the absorber is constant during some time interval. The big problem in this, to do this properly, is to account for the fact that after having a lot of transfer events with different energies, your temperature might start to change and develop fluctuations on a slower time scale. And then you need to take into account, when you calculate the statistics of the temperature fluctuations, that you also have to worry about that your temperature that you are looking at is fluctuating over time, which modulates the rates over time for how to jump in and out. So it becomes a rather complicated problem with a fluctuating variable which governs the individual rates. And this is something we can solve using a certain technique, a stochastic path integral approach. I'm definitely not going into the details here, but you can solve this under some assumptions in a saddle point type of equation approximation and get out results which allow you to predict what's going to happen physically here. So here are just two examples which tells you essentially that if you try to bias your system by applying a temperature to your superconductor, what you see here is essentially that if you heat your superconductor injector, your temperature distribution of the absorber will be shifted to higher temperatures. And if you instead would cool your superconductor, it will be shifted to lower temperatures, which is not so surprising. And then we compare this to Gaussian fluctuations and notice that your temperature fluctuations will actually be non-Gaussian, which isn't, well, anything which is non-Gaussian is interesting because Gaussian would be your first guess what's happening. But this is again a little bit on the technical side. We can do some calculations of the individual cumulants. And one point I would like to stress here, like the first cumulant is that you can measure you can get some information about the average temperature. You will get an equation for the energy flows in and out of your system, which you have to solve. numerically, and from that one you can get your time average temperature. That is something they measure in experiment. The next thing, which is now actually has never been measured and is now being studied and hopefully successfully measured in the lab in Aalto, is the fluctuations, which are the low frequency fluctuations. So this means that you are actually looking at the fluctuations of your temperature signal and say how much is it fluctuating, and then you get a estimate of the width of these fluctuations, the magnitude of the temperature fluctuations. And that is something that has never been measured, and in order to do that you really have to have the sensitive equipment that they have. So you can resolve these fluctuations over time, and that you can really register them sensitively enough so that you can separate this fluctuation due to the transfers of electrons from the overall background fluctuation that comes from everything that you have in your system. So that is something we can predict. Then you can also go higher up, and this is maybe a little bit outside the scope here. So we did these calculations. Here are some details. It just tells you that if you are applying a temperature and heating your superconductor injector, then eventually nothing happens until you reach a certain threshold where your kBT times the temperature of a superconductor becomes comparable to the gap, and then you have a strong onset of the temperature in your absorber. If you instead do a voltage bias, you actually have an opposite thing, which is known in the field because you have cooling. So if you apply finite voltage bias, at some point you actually start to cool your absorber, the average temperature, so it goes down as a function of voltage with respect to the gap here. So these things comes out as we expect them to do. We find these breaking points where the values go from being essentially undisturbed to something happening. We can calculate this TS star and V star as kind of the limits where things start to happen. So that's also nice to know experimentally where things start to take off from the basic values or the unperturbed values. We can do it for the noise. We can predict that you will have some peak in the noise if you increase the temperature of your injector. And we can, if I go this a bit fast here, you can have a dip in the noise going from some large value to suddenly going down when you increase the voltage bias. And this is actually related almost entirely to the fact that your thermal conductivity, which sits in the denominator of your noise expression, becomes very large when you have a large enough bias, because particles can escape out over the superconducting gap, and you have a much larger thermal conductivity, and therefore the entire noise is suppressed. So this is also something that they should look for, a clear shift from a rather high noise to a noise which becomes very small when you reach a certain voltage. The third cumulant I don't really say much about, and I just see that my time is out, so I land on the conclusions. So summarizing a bit, in the first part I wanted to give an overview of single energy quantum calorimetry, let's say what the idea is and how the field experimentally and also theoretically are narrowing in on the idea of measuring individual particles, electrons, microwave photons, individual phonons, you name it, that you can detect by seeing how much energy they deposit by looking at the temperature spike. That would be great if you can do this on nanoscopic energy scales below 1 milli-electron volts, let's say. So that's the holy grail in this picture here. And then I also said that, well, we realize it's not easy, so let's, as a first step, try to characterize, look at the device we want to use for the calorimetry, and let's try to characterize the fluctuations that inevitably are there when you want to do things on this low temperature, small energy scale, and try to learn something as a first step towards this calorimetry. And then it was a description of the system we are talking about, and then I used this somewhat technical approach to calculate not only the average flows and the fluctuations, but the full statistics of everything you can have here. And then we also had some estimations of parameters and which voltage bias, which temperature you need in order to start to see some effects, and where you should go for these properties of the fluctuations that you would like to learn about. So this is the first step, and what we are hoping now, this was a theory paper published. There are experiments ongoing in Aalto. Hopefully there will be an experiment where one can study these fluctuations as a function of applied bias and temperature. And if we know what's coming out and we understand that, we might need to go on and extend this model a little bit. There seems to be other mechanisms. For example, there seems to be photons in the game here, which are transporting heat. There seems to be superconducting proximity effects and other stuff that we might need to worry about to describe this better. Okay, thank you very much.
What would be the differences if you use a normal conductor instead of a superconductor?
Instead of a?
Instead of a superconductor,
Yeah.
you use a normal. What will be the difference? How is it?
Right. So, okay, so this I maybe didn't say. Let's see if I can go back. The property of a superconductor for an injector is that it has a spectrum with a gap in it. So what this means is that you have no free particles inside the gap in the spectrum, and your lowest energy quasi-particles, electrons, holes, are delta up from the chemical potential. So this means that you are creating a lower bound on the energies that you jump into the system. The good thing with this is that if you are afraid of that you cannot measure low energy things, if you have a normal metal here, there will be not this type of gap. So then you can have energies going all the way from 0 all the way up with some distribution going in, and the lowest energy particles, you would have no chance. They will completely drown in the background of all the phonons. But here you can have a hope of separating the high energy events due to your injector, I mean high energy in this context, compared to the low energy events which are taking place between your absorber and the bath. Was this an answer to? Yeah. So that's the logic behind that. Yeah.
So the practical analog of this heat capacity is the capacitors, right? The electric capacitors.
Yeah. So
now, when you go nano, we know that the electric capacitor has two cells, right? One is classic Stochastic geometry, and the other one is, let's say, more quantum. It depends on the split states.
yeah.
Can you do the same?
I'm pretty sure you can. I don't really know how this looks. I mean, this you probably even know better. So this is a very classical model of how the energy behaves after it lands on your absorber. So there's no quantum in that process actually. So some people would maybe say, well, quantum calorimetry, it's a heat pulse carried by a quantum particle, but that's all the quantum there is, right? The rest of my model is actually a semi-classical or classical model. So there's no quantum effects in the detection of the temperature here. I assume that there's a temperature, and I know that there's a classical, there's a heat capacity. I don't really care where it comes from. But essentially what I do when I calculate it is that I'm using the textbook for a fermionic, liquid theory, three-dimensional fermions, and then I get something which is proportional to temperature, density of states, etc., etc. So here I don't really introduce that. But I think that if you would like to change the material of such a capacitor and maybe do a two-dimensional semiconductor or a graphene sheet, then it becomes smaller C, more sensitive, but also a need of thinking about other effects. So I agree with you. That's a good point. I didn't really think about how that would look, but it should be there, I think so. Yeah.